Well, hello, Nick here, and long time no see, eh? And well, welcome to my new shack in my new QTH, which is kind of why you've not seen me post any videos for months and months, because I've been moving house and unpacking and all the rest of it. And I didn't even have a workbench to build anything on, but I'm in now and I've fired up the soldering iron again, so it's all good. And so for this video, I wanted to return to something I've been threatening to do for ages and I've never actually got round to doing, which is to look at the dark art of the band pass filter. Oh yes, be afraid. Be very afraid. Now, in case you're thinking, just a minute, and this guy covered all this stuff before. Didn't I do like a 3-part series on LC filters? Yes, I did. But actually, when I did that, I was building a high pass filter, and a high pass filter, along with its brother, the low pass filter, are more forgiving. They're easier to build. They're more tolerant of different kind of component values, and you don't have to build them all that carefully. It's probably going to work. You can follow the design, and you've got a fair to middling chance of it actually working. These bad boys are not forgiving at all, and by their very nature, a band pass filter, you've got to have some means of actually controlling it, where that pass band actually comes. And really, with a band pass filter, it's almost an impossible dream, because you've got all these different things that you want out of it. So you want to pass a bandwidth. So now in this case, I'm building one for the 17 meter band, which is actually a very narrow bit of frequency. So you want it to pass your frequencies relatively unattenuated, and then you want to attenuate the heck out of everything else. So you want the skirts to be as steep as you can get. You want it to have a good impedance, which to match 50 ohms either side of it, which will give it a good SWR, and crucially, you want it to have a low insertion loss, so that's the actual attenuation of the signals going through it. And really, you've got these two competing things which don't play nicely together, I'm afraid, which is to have a narrow bandwidth, so a high Q, basically, and you can do that, but the narrower the bandwidth gets, the higher the insertion loss. So you lose more of your signal that's actually passing through it. So and there's nothing you can do about that. It's just this compromise. You can't have them both. You can't have a very, very narrow bandwidth and a very low insertion loss. So what I end up doing is settling for a kind of wider bandwidth than I would like, really, but just so I can have lower losses going through it. And but you'll see all of that because we're going to take a closer look at it, and the design. And it is a very simple thing. There's not very many components there, but they can be tricky to do. So to be able to build these things is a useful skill. So that's enough of my waffle. Let's take a look at it and see how I got on. Okay, so here is the design which I used, and full disclosure, this is a very common design for bandpass filters. It's the one I come back to time and time again, so it's certainly not original to me, far from it. And actually, this particular design I owe to Hans Summers of QRP Labs fame, and when I first built a radio receiver that needed a bandpass filter, I bought a kit from Hans and built one there. So you get all the parts, you still have to put it together and tweak it. But what's brilliant is he gives you these brilliant instructions, which you can actually download freely off his website, which are very detailed and absolutely brilliant when you're starting out. And actually, you could do worse than buying one of Hans's kits if you've never built one of these before, just for the instructions, if nothing else, because they're excellent. So, but what's particularly useful is some of his component values and turns ratios and things, which I've built many bandpass filters to his specifications, although I usually have to adapt them a little bit. So this is a bandpass filter for 17 meters. So as I said, it's a very narrow band, 18 decimal 068 to 18 decimal 168 megahertz. So there's not a lot there, just 100 kilohertz. But essentially what you're looking at here is two parallel tuned circuits. Now this one's technically a transformer because you've got a primary winding with quite a few turns on it, and then a fewer turns on a secondary, and that's just to couple it for 50 ohms to the outside world. But essentially this inductor here and this capacitor here form a tuned circuit, parallel tuned circuit, and you'll notice identically here, this one here and this one here. And well, when I say this one here, actually it's both of these. In truth, this 30 picofarad capacitor is a trimmer, as is this one, and so you've got, so this is all the parallel capacitance, these two in parallel with each other, but this one is variable, which is really important because that will determine where your passband sits by tweaking this one and this one. And so that's really important to have some control over that. Now this 10 picofarad here, this is another trimmer because the actual real amount it calls for is much lower than that. It's like 3 or 4 picofarads. But I found this is the coupling capacitor, and this is really important because this couples this tuned circuit with this tuned circuit, and this will have a great bearing on your bandwidth, how wide the filter is, and as I've said, you know, what the insertion loss is. So this one you need to tweak, and you can get the filter shape right and get it nice and flat. It's a Butterworth design, so there's not a lot of ripple as you get with the Chevy ones. But you have to accept that your skirts won't be as steep as you would with like a Chevy design. But I've used this Butterworth design very successfully in the past. So yeah, it seems to work well. So it actually, it's not a lot really. This is one, you'll see in a minute, but one toroid, a little yellow 37-6. With a primary winding there with well, it was supposed to call for 19 turns. I ended up putting 16 on it and 3 turns on the secondary, which connects to the BNC connector then coming in. Incidentally, this is an LT Spice simulation, so I mean, you can ignore the signal source and ignore this 50 ohms. That's just simulating a 50 ohms load. And yeah, so 3 trimmers, 1 trimmer there, 1 trimmer there, 1 trimmer there, and then 2 separate capacitors and 2 little transformers. Yeah, so let's see what it actually looks like in reality. Right, so here is the finished product. I like to use these little metal kind of Altoids like tins. That you've just got room to install a BNC connector on either side, and just enough clearance with the lid coming down there. It's a bit tighter there. So how I do that is I start with the lid on, and you estimate basically halfway down, and then just go down a little bit with a bradawl and make a hole in there. And then I've got a stepped drill bit, which are absolutely brilliant. And so I can't remember what number it is, but it was the 3rd step on the lowest setting, is just about the perfect size for a BNC connector. And then I go in with some long nose pliers and just prise it open a little bit more, otherwise it's a little bit tight. You want it fairly tight when you put it in there, but not too tight. You can't get it in.
Okay, so here is inside the filter. I'm just going to zoom in a bit here. And so essentially you can see I've got two conductive pads in the middle there. And I won't go into the details of how I do this, just look at one of my other videos, but it's done with the Dremel. You just kind of engrave it out. And I wanted two longer pads so I could hang some components off those traces, and I've tinned them, well, almost entirely. And I started off with that little white trimmer. That's the coupling capacitor that I mentioned a moment ago in the middle. And then I put the two 30 picofarad trimmers at the top, you'll see there. And then the separate capacitors are hanging off the bottom, and then you just got the transformers. Now, if you're wondering why the wire is rather long going into the primary, it's because I wound this originally with the 19 turns in mind, but I ended up taking 3 turns off. And actually, it was just easier rather than taking the whole thing off and stripping it down and scraping all the enamel off and tinning it. Again, I couldn't really be bothered, to be honest. So it works absolutely fine as it is. And so you see, I've basically gone in on the secondary straight to the BNC connection and soldered that straight in there. Both grounds go together and to the ground plane. Very important to remember to ground your actual board to the chassis. You don't need to bother about the little ground tag on the BNC, because by virtue of screwing it through that metal tin, the whole thing's grounded. But sometimes I've forgotten to actually ground the board and wonder why it doesn't work. Yeah, but if you do that, it should be all right. I ended up with 16 turns and on the primary and 3 turns on the secondary. And that works really well. Now, actually, when you're doing this, or if you're doing any of these, this configuration is quite a good one, because you will probably have to faff around a bit with the coil. Even though I'd measured out as close as I could the amount of inductance it said I needed, turns out I needed less. So, and that will be a multitude of different things, other stray capacitances and other stuff as well. How tightly I wind the coil, etc. There's quite a lot of variables, but that's okay. And you can only get so far in terms of where your bandpass filter sits by adjusting those two 30 picofarad trimmers. You'll know, because you'll see, you'll be able to move it by adjusting those two. You'll be able to move it across, but you'll get to a point where you can't move it any further. And if it's still too far on the left, then essentially it's inductive, and you've got to remove some of that inductance. And so taking a turn or two, in my case 3, off the coil did the trick and brought it into alignment where I wanted it to be. So doesn't take too long to build. It's not the prettiest bit of soldering in the world. I need to for some reason I've got the thundering big tip on the iron at the moment, and I thought I'll just go with that. But that's fine. That doesn't matter. It's going to have a lid on it anyway, so you're not going to see it. And the wonderful thing is, once you've tweaked it, you can put the lid on it and forget about it. What I did do before I put the secondary turns on these transformers, you won't be able to see, but I got some of that kind of that UV welding stuff that you kind of gloop it on. It's like a kind of glue, and then you kind of seal it with this UV light, and it sets like concrete. So I did put a bit of that on both sides just to hold those thinner wire turns on, because what can sometimes happen is you can get your turns on, it all looks great, but once you start putting that thicker wire for the secondary on, it messes up all the work underneath. So I kind of anchor the the thinner wire down. I didn't bother anchoring the thicker wire down because, to be honest, it's so thick, that wire. Once it's actually soldered down, nothing's going to move. It's really solid, which is fine. Right, okay. So and how you adjust it is with a screwdriver, or two different screwdrivers. As I said, the 30 picofarad trimmers at the top. As you twist that slowly to the left or to the right, you'll see your filter shape move across the screen of your Nano VNA. If that's what you're using, that's what I used to test. This is what I use all the while now. And the little white trimmer, the 10 picofarad trimmer in the middle, is what you would use to actually adjust the coupling and the shape. And you can kind of just get that so it looks right. It's in the right place, and it's got the right insertion loss.
So the question you're probably wondering about is, how good is it? How well does it work? Well, see for yourself. Now, what you're looking at here is a screen grab that Hans Summers provides of his kit, the one he builds, and he builds them for all the HF bands, or at least he provides the kits for you to build them. I should say. So that's what his look like, and this that's a screen grab from his spectrum analyzer of one that he made, and this is the one I made, and I put in the same parameters so you could see, and I think if you'll agree, not bad at all. You'll notice mine is wider, particularly the further you get down, the wider mine is. But there is an advantage in that as well, which you probably can't see too well on this, but you will do in a moment. But in terms of the shape, yeah, fantastic, and where I wanted it to be, brilliant. But let's have a look at it more closely, and you'll see what I mean. So obviously it's a photograph of my Nano VNA, and you will see there that it is nice and flat, and yeah, it's a bit wide, but if I go in, that's a span of 10 megahertz. If I go into half that and do a span of 5 megahertz, which is here, you'll see just look at that. So it's set, marker 1 is at 18.118 megahertz. But just look at that top left, the insertion loss, minus 1.04 dB. That's really very good indeed. Particularly if I tell you that on Hans's published results that he puts on his website, his minus 3 dB bandwidth is 1.63 megahertz. So that's the width of the bandwidth of the filter measured at minus 3 dB from the peak. 1.63 megahertz. Mine is 1.7, so mine's a bit wider. And as you can see, it gets wider the further down you go. But his insertion loss is minus 1.95 dB, so nearly minus 2 dB. My insertion loss, as you can see there, but averages over that minus 3 dB span to be minus 1.05. So 1 dB better, which is at the expense of a wider filter, which is what I was saying before. But I'm really pleased with that. And if you look at that marker, the actual whole of the 17 meter band fits into that flat bit at the top of the filter. So yeah, so really very pleased with that. Just a few other stats for those that are interested. The impedance measured at the ports of the device, 48 ohms. Well, you can't complain at that really, which gives you obviously 48 ohms, a very low voltage standing wave ratio. So the SWR is 1.0, well, between 1.05 to 1 and 1.07, so very, very good. And as I said, the insertion loss is between 1.04 and 1.07 dB. So yeah, very, very pleased with that. Very pleased with that. And the next thing will be in due course to build the rest of the radio that it's going to be a part of. Well, there you go. Hope that was of some interest, and perhaps maybe even encouraged one or two folks to have a go at homebrewing their own bandpass filters. But thank you very much for watching, and catch you again on the next video. Bye bye, 73.